The case for nuclear power. As concern about global warming grows, the race is on to find reliable alternative sources of power to replace fossil fuels, which produce greenhouse gases. Nuclear power generation is clean, but many people think it's not a safe option. Would public feelings change if a system was available that would never have a meltdown and which burnt old radioactive waste as part of the power generation process? Here to explain the need for this new technology is Dr. Simon Patterson.
Thank you. Now, when it comes to discussing energy, for most people, the word nuclear, it's not something you talk about in everyday conversation. And it's certainly not something you suggest to solve the problem of increased energy demands. Even though nuclear energy can produce large amounts of electricity without increasing greenhouse gases, most people consider it too dangerous and environmentally damaging. It's seen as a necessary evil we should try and do without. Today, though, I'd like to briefly review the problems of climate change and existing energy production. Then I'd like to give you a positive case for nuclear power, and in particular, a new type of nuclear power using thorium-fueled reactors. Now that's thorium spelt Thorium. So let's go to my first point then, and that's climate change. We know climate change is happening, no doubt, and most people accept the research that shows human activity is greatly contributing to warming the planet. The results of this warming are becoming more and more evident, from melting polar ice caps to extreme weather events like hurricanes. Just recently, a study in the journal Conservation Biology stated that global warming will become a leading cause of extinction from the tropical Andes to South Africa, with thousands of species of plants and animals likely to be wiped out in a matter of decades. Now, all this comes at a time when the world's demand for energy is huge. Our civilization uses more energy now than at any time in human history. Energy demand in advanced economies has risen 10% since 1990 and a whopping 59% since 1967. And yet, many of the most populated nations on Earth have yet to reach the peak consumption levels we have in the industrialized world. Of course, I'm thinking here of China and India. As their industrialization increases, they will have far greater energy requirements as the developed world because of their huge populations. And of course, everyone has been asking where all this energy is going to come from. Where's it going to come from? Coal was historically the foundation of European industrialization and is by far the cheapest and most abundant energy source. Australia produces nearly all its power from coal, but coal is also one of the biggest contributors to greenhouse gases, particularly carbon dioxide. And carbon dioxide stays a long time in the atmosphere. It's estimated that 56% of all of the CO2 ever generated by humans burning fossil fuels is still in the atmosphere. It's estimated that this is responsible, directly or indirectly, for 80% of all global warming. Surely we should not continue to build coal-fired power stations. However, China alone is planning to build another 544 coal-fired power stations over the next 2 decades, and India is planning more stations as well. So, with the obvious damage to the environment caused by coal, I think it's time to consider any form of power generation that does not make global warming worse. So let's look at all the alternatives. Firstly, in an ideal world, we would all rely on solar or wind energy because they are, in practical terms, limitless. However, these are unreliable for baseload power, which is the backbone of any electricity network. So, let's look at baseload power. When we get up in the morning and turn on the lights, we expect the power to be there. If it isn't, we don't shrug and say, "Oh well, no wind today." Without dependable on-call electricity, our factories and offices would grind to a halt, our economies would suffer, and our cities would become dysfunctional. Also, while solar systems are being developed, we still lack the capacity to store this periodic energy. In practical terms, the cleanest form of baseload energy is hydroelectric power. But most of the world's easy-to-dam rivers are already tapped. Besides, flooding valleys to create dams has a negative impact on biodiversity and would require the movement or destruction of existing communities and increase environmental damage in other areas. Okay, so this then brings me on to the second part of my talk today, and that is the case for nuclear power. Nuclear reactors have generated billions of gigawatts of baseload power whilst emitting no greenhouse gases. Despite the public concern over safety and radioactive waste from accidents like Chernobyl, nuclear energy has an extremely good safety record. Let me explain what I mean. In the 55-year history of nuclear power generation, fewer people have died from its use than are killed every week by coal. Mining coal kills more than 10,000 people a year. But the number of deaths associated with burning it is even worse. The Earth Policy Institute in Washington, D.C. estimates that air pollution from coal-fired power plants accounts for 23,600 US deaths annually. That's 23,600 deaths in the US alone. As well, an estimated 554,000 asthma attacks, 16,200 cases of chronic bronchitis, and 38,200 non-fatal heart attacks each year. They're big numbers. We worry a lot about nuclear waste buried deep underground, but we don't worry about the coal waste we breathe in the air or the radioactivity of coal ash that's left over from burning this very nasty fossil fuel. So, even conventional nuclear power looks good in comparison with coal. But what if we could generate nuclear power with a reactor that would never suffer a meltdown, that produced no weapons-grade byproducts, and that even burned up old radioactive waste as part of the process? Such thorium-fueled reactors are theoretically possible, with the most attractive candidates called accelerator-driven systems. Accelerator-driven systems. Now, conventional reactors have uranium or plutonium in the core and are effectively an atom bomb trying to blow up. The extraordinary heat created is used to drive a turbine and generate power. But an accelerator-driven thorium system is different. No matter how much thorium you put in the core, it can never blow up. They make lousy atom bombs. But attach an accelerator to the core, cook it up to a critical temperature, and you have a nuclear power source. This completely changes the physics of nuclear reactions. It means that a fraction of the waste is generated, and all of it is radioactive for only 500 years. That's a lot better than the conventional reactors with their 10,000 years of life in their waste. More importantly, it burns old nuclear waste in the process. Imagine destroying old nuclear weapons stockpiles, as well as other intractable radioactive waste, while generating power, and more importantly, not spewing out tons of greenhouse gases, as other forms of baseload energy generation do, oil and gas technology included. Accelerator-driven thorium systems look very attractive to a world desperate for more energy, but needing to dramatically reduce its greenhouse emissions. A lot of the basic science of these reactors has already been done in Russia, India, and Germany. And while there's no full-scale prototype in operation, they look safer as an alternative to today's conventional reactors. In conclusion, let me give you my main points. We have a global demand for energy, and traditional coal and oil-based technology is going to lead to environmental disaster. We know that. We're not going to solve this problem with alternative renewable technologies anytime in the near future, as they are periodic and do not provide the necessary baseload needs. These days the world is too complex, the decisions too important, and the implications too far-reaching for us not to listen to the best scientific advice available. Nuclear technology is a relatively safe technology, and there are a range of nuclear technologies out there, like accelerator-driven thorium systems, that are looking really promising. We need to encourage our politicians and business leaders to investigate these options. We need to do this while we still have the time. Thank you. We need to encourage our politicians and business leaders to investigate these options. We need to do this while we still have the time. Thank you.